Hello everyone. I've been planning this video for a long time. Please watch it without skipping, because I tried to create a film that serves as an educational guide, but at the same time is interesting and easy to understand for a wide audience. I would really appreciate it if you could comment on the video to show your support, rate it, and if possible, share it with your friends. A lot of time and effort went into making this. In it, I will talk about processes that are simple and at the same time extremely difficult to understand, but I'll do my best to explain everything clearly. These are fascinating processes that we encounter every day, but at the same time, they have a complex nature. From the history of great scientific discoveries to the mystical world of quantum mechanics. So get comfortable. We're about to begin. The semiconductor diode. You'd think, what could be simpler? The good old diode with a single PN junction, which conducts current well in the forward direction and hardly at all in the reverse. Of course, diodes come in all sorts of varieties. Low frequency, high frequency, and even ultra-high frequency diodes. They differ in current, voltage, reverse recovery time, and so on. For a classic silicon diode, the forward voltage drop is about 0.6 to 0.7 volts, and it increases as the current flowing through it rises. There are Schottky barrier diodes, where this value is around 0.2 volts. There are photodiodes, which, when the crystal's illuminated, generate light. There are LEDs, whose crystal starts to emit light when current is applied. There are Zener diodes, which, when reverse biased, enter the breakdown mode at a certain voltage, thereby stabilizing it. There are suppressors, which are used in particular for protection purposes. Laser diodes, whose purpose I think everyone knows. Among the wide variety of semiconductor diodes, there is at least one in which processes occur that can still spark heated debates among scientists even today. A diode whose operation cannot be explained by the principles and laws of classical physics because the nature of its function is not from our world at all, but delves into the complex quantum realm. And that is the Esaki diode, or tunnel diode. Today, I'll try to immerse you in the nature of this fascinating phenomenon. Without overloading you with theory, I'll do my best to explain why this component is so unique and how it works, where it is used, why it was created, and I'll also show how it works with a real-life example. So how does the quantum Esaki diode work? Let me start right from the beginning. In front of you is a cut of hill, what's called a barrier. And here's a ball rolling across the table that encounters a potential barrier in the form of this hill. What are the chances that the ball can overcome this barrier? It could go around it, but let's assume that's impossible since there are no paths to bypass it. If it had enough energy, the ball could reach the top of the barrier and roll down the other side, but let's assume it doesn't have enough energy for that. In our world, the ball would have to turn around and go back since the path is blocked. But what if I told you that the ball could simply end up on the other side of the barrier, literally disappear and teleport to the other side? Sounds crazy, right? But actually it's not. The beginning of the 19th century, specifically the year 1801, Aland, one of the greatest scientists of that time, Thomas Young, conducts an experiment with light. He placed a barrier with two identical slits in front of a light source, and behind it he set up a projection screen. According to the main theory of that time, light was a particle. This was asserted by none other than Sir Isaac Newton himself. Therefore, on the projection screen, Young expected to see two parallel bands of light. This would be the light that passed through the slits, and a dark area between them, but what actually happened was completely different. Young saw a series of alternating interference bands, which was a property of the wave nature of light. At that time, Young didn't know about photons, but with this experiment, he proved the wave nature of a phenomenon like light. Almost 130 years later, in 1927, two American physicists, Clinton Davison and Lester Germer, conducted an interesting experiment. Inside a vacuum chamber, they placed an electron source and a nickel crystal, which was bombarded with electrons. A diffraction pattern of the reflected electrons was observed on the receiving screen, which matched exactly with the calculations based on de Broglie's wavelength. This became the first direct experimental confirmation of the wave nature of matter, showing that electrons, like light, have a dual nature and can behave either as particles or as waves. It would seem that everything is obvious. A beam of the tiniest particles behaves like a wave, and that should be the end of the story. But it's not that simple. The thing is, these two experiments have been conducted many times, including with detectors that record the passage of particles through the slits in the case of Young's experiment. The detectors recorded that each particle, including photons, passes through only one slit, like a classical particle, and never through both slits, like a wave. And the whole mystery is that if you observe the particle and record which slit it passes through, these guys no longer behave like a wave that creates an interference pattern on the screen, but like a classical particle, resulting in just two bands on the screen. The same thing happens when observing the Davison-Germer experiment. In other words, observation from the outside destroys the entire wave nature of particles, while without observation, this property appears. This kind of behavior demonstrates the principle of wave-particle duality. It's a property of nature where the same tiny objects can display the characteristics of classical waves under some circumstances, and those of classical particles under others. This phenomenon is commonly called the observer effect. The very act of measurement already affects the result. 100 years after the birth of quantum mechanics, we still can't fully answer the question of why this happens. Perhaps the key to the mystery lies in the deep equations of quantum field theory, such as the Yang-Mills equations and the mass gap problem, which is considered one of the 7 Millennium Prize problems in mathematics, but apparently we'll have to wait a long time. So far, only one of them has been solved. The Poincare conjecture by the modern genius Grigori Perelman. A prize of $1 million is awarded for solving each of the 7 problems. Perelman, by the way, refused it, just as he did all other awards and prizes. You might ask, why did I give you this lecture, and what does it have to do with a tunnel diode? Well, first of all, you learned a lot of new things, or refreshed your memory. And secondly, without understanding the above, it's impossible to grasp how a tunnel diode works. So, with your permission, I'll continue the story. At this point, we already know that a particle can behave in a classical way or a wave-like way, depending on the circumstances. We smoothly transitioned into quantum mechanics. All you need to know at this stage is that one of the foundations of quantum mechanics is the concept of quantum superposition. The essence of this concept is that a particle can exist in an infinite number of possible locations until we observe it, and its final position is determined only at the moment of our observation. Therefore, it can be said that the act of observation leads to the selection of one of the possible states and to the collapse of the wave system. This phenomenon is perfectly illustrated by Schrödinger's code, a code that is both alive and dead at the same time. But we won't know which until we open the box. Schrödinger's code is, of course, an abstract concept demonstrating the transfer of phenomena from the quantum world into ours. But there is some truth to it. It is precisely such abstract quantum paradoxes that form the basis of a very real device, the tunnel diode. A tunnel diode is essentially an ordinary diode. It has a p-n junction. Both regions are heavily doped or supersaturated with impurities, containing a large number of charge carriers, electrons and holes. With such a high concentration of carriers, the width of the depletion region, that is, the barrier itself between the regions, becomes very narrow, just a few nanometers. From the perspective of classical physics, an electron cannot overcome this barrier if its energy is less than the height of the barrier. So, what can an electron do if it really wants to get to the other side of the barrier? That's right, it can enter the quantum world and remember that it's not just a classical particle, but also a wave. An electron shouldn't be thought of as a physical particle like a little ball. It's an entity that has properties of both a particle and a wave. It has energy, but it's actually a quantum of matter described by a wave function. Earlier, I mentioned that in classical physics, an electron can't pass through a barrier if its energy is less than the height of the barrier. In quantum physics, the wave function doesn't just stop, it actually penetrates a little way into the barrier. Although most of the wave fades out inside the barrier, a small part of it seeps through to the other side, giving a non-zero probability that the electron will end up on the other side. So it's not energy that flows through the barrier, but rather the probability of finding the electron there, which means that sometimes it really does end up on the other side of the barrier, even without having enough energy for it in the classical sense. This is the quantum tunneling effect, which is exactly how a tunnel diode works. In fact, it might seem to you like impossible nonsense, but the effect has long been studied and is mathematically described by the Schrödinger equation. The equation shows that the wave function doesn't just stop, but instead decays exponentially inside the barrier. On the other side, there remains a non-zero amplitude, which means there is a non-zero probability of finding the particle on the other side. Now, let's move from theory to practice. In circuit diagrams, the tunnel diode is often depicted with the symbol shown. It's important to emphasize that the tunneling effect only appears at a certain voltage across the diode. We have a load, for example a resistor, and a certain voltage is applied to its terminals. As this voltage increases, the current flowing through it will also increase. This is Ohm's law, but in a tunnel diode, the following happens. If we increase the voltage, the current increases as expected. But when a certain voltage is reached, something strange happens. The current drops sharply, and as the voltage continues to increase, it decreases even more. So does this process contradict Ohm's law, or even disprove it entirely? I would really like to say that there's no way around Ohm. And here, within a certain voltage range, we are dealing with differential resistance, which can actually be less than zero, but Ohm's law is still not violated and continues to describe the relationship between current and voltage. But there are some nuances here. Ohm's law describes a linear relationship, and in semiconductors that's a whole different challenge. Just like in a number of other situations, Ohm's law may only partially apply or not apply at all. I'll leave this question open so you have a chance to discuss it in the comments. Let's get back to the tunnel diode. If we keep increasing the voltage, the current will start to rise again. The final formulation describing how a tunnel diode works could look like this. At a low forward voltage across the diode, electrons tunnel directly through the narrow barrier. The current starts to increase. In other words, tunneling happens specifically at this stage, at low voltages. You could say this current is the tunneling current. It's also important to emphasize that the barrier is extremely narrow, which increases the probability of tunneling. The narrower the barrier, the higher the probability. Tunneling is possible when the occupied levels in the conduction band of the N region match in energy with the available levels in the valence band of the P region. Because of the very strong doping, these regions end up at the same energy level, so the electron can tunnel through the narrow barrier without acceleration, without losing energy. As the voltage increases further, the band levels no longer align, tunneling weakens, and the tunnel current decreases, resulting in a region of negative differential resistance. In other words, the aforementioned levels move apart, the energy alignment disappears, and the electron has nowhere to jump on the other side, so the tunnel current decreases. The voltage is increased even further, the regular carrier injection mechanism kicks in, and the current will start to increase naturally. That is, on the current voltage characteristic of a tunnel diode, there is a certain section that's commonly referred to as the region of negative differential resistance. It's called that because the current voltage characteristic has a negative slope in this region. This section appears when tunneling, which provides current at low voltages, begins to weaken. In practice, this region allows for the generation of oscillations and, for example, makes it possible to build an LC oscillator using a tunnel diode. In its simplest form, such an oscillator would look like this. It consists of a power source, the tunnel diode itself, an LC circuit, and several resistors. The power supply, in this case 1.5 volts, is applied to a voltage divider. These very resistors set the voltage across the diode and are chosen so that the operating point falls within the region of negative differential conductivity. That's what makes the magic happen. With further changes in voltage, the current changes abruptly. The oscillatory circuit has its own resonant frequency. In the region of active tunneling, the current through the diode is high, and it charges the circuit's capacitor. Then, when the diode enters the region of negative differential resistance, the current drops sharply and the capacitor begins to discharge through the coil. At this moment, oscillations arise in the circuit. The polarity of the voltage across the capacitor changes. At first it's direct, then, due to the coil's self-induction, it becomes reversed. The tunnel diode sustains these oscillations. At the moment the current drops, the LC circuit receives an energy boost and continues to oscillate. It's important to understand that, initially, there are micro-oscillations and noise in the system. The process of charging and discharging the capacitor changes the voltage in the system, creating surges and jumps, which leads to changes in the current through the tunnel diode. In other words, you could say the diode and the circuit support each other's operation. With a ready-made oscillator, nothing stops you from building a radio signal transmitter based on it. Back in the day, I used to tinker with transmitters like these, and I even have a few articles left on the soldering iron website. Right now, you're looking at one of the simplest versions of such transmitters. Of course, it works and even broadcasts. I won't focus your attention on the construction itself, but if you're interested, I can make a separate video about transmitters using tunnel diodes. Tunnel diodes have been used in many different applications, for building fast logic circuits and transmitters, oscillators, amplifiers, and so on. How they work depends on where the operating point is located on their current voltage characteristic. In the region of negative differential resistance, the diode generates oscillations. At the boundary, it amplifies, and at the transition between states, it switches. But the question about the complications with tunnel diodes remains open. Why do we need it if everything mentioned above can also be built using transistors? The answer to this question takes us back to 1957, when Japanese physicist Leo Asaki invented the tunnel diode, for which he would receive the Nobel Prize 16 years later in 1973. By the way, Asaki's still alive. He turned 100 years old this year. So the transistors of that era, the late 1950s, could operate at frequencies of tens or hundreds of kilohertz. In rare cases, the frequency exceeded 10 megahertz. The switching time of these dinosaurs was quite long. But the tunnel diode is capable of switching quickly, extremely quickly, in less than a nanosecond. For it, cutoff frequencies in the tens and even hundreds of gigahertz were achievable, which made it possible to use them in cutting-edge long-distance communication equipment and in ultra-fast logic circuits. The operating principle of a regular transistor is based on the movement of charge carriers through the bulk of the semiconductor, while a tunnel diode works through instantaneous tunneling without diffusion. That's why, in terms of speed and frequency, tunnel diodes had no equals, not even close. But after a couple of decades, everything changed. New types of transistors appeared that could operate at those frequencies. And nowadays, transistors have long since surpassed the terahertz frequency barrier. Transistors are more efficient, easier to control, their behavior is predictable, and their operation is easy to stabilize, unlike tunnel diodes. That's why these old-timers have since retired with honor. A tunnel diode is a rather finicky thing. It's sensitive to high voltage exceeding the tunnel current and static electricity. Even a routine check with a multimeter can kill it, so you have to handle it with the utmost care. People may have forgotten about tunnel diodes, but quantum tunneling is still very much being studied. On December 10th of this year, the Nobel Prize award ceremony will take place. The physics prize will be awarded to John Clark, Michel Devore, and John Martinez. Can you guess what for? Yes, for yet another contribution to quantum mechanical tunneling. More precisely, for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electrical circuit. The fact that electrons can tunnel has been known for a long time, but these guys showed and proved that quantum tunneling can manifest not only at the level of individual electrons, but also in macroscopic electrical circuits containing a huge number of particles. Like everything quantum, this phenomenon is also not easy to explain, but to put it briefly, it was proven that the macroscopic wave function of the superconductor is involved in the tunneling. The phase of this function tunnels, not individual electrons. Moreover, all of the above was proven back in the mid-80s by the aforementioned scientists, but they received the Nobel Prize 40 years later. One of the main platforms for modern quantum computers is superconducting qubits. Essentially, these are quantum bits that, unlike regular bits, can exist in a state of superposition. Superconducting qubits are created based on Josephson junctions. In quantum circuit mode, these junctions are used precisely because they exhibit macroscopic tunneling and energy quantization, which were experimentally studied by Clark, Devore, and Martinez. This discovery forms the foundation of all modern superconducting quantum technology. Qubits, quantum computers, quantum sensors, amplifiers, and artificial atoms. Well, hope you enjoyed the video, or at least didn't find it boring. Honestly, I did my best. If you'd like to see more videos like this in the future, let me know in the comments. I track the relevance of topics based on the comments. The more positive feedback and constructive criticism there is, the more actively this kind of content gets promoted, which helps new videos come out. So I'm asking for your help in promoting this video. That's all from me for now. As always, this was Cassiano K with you. See you next time. Bye.